Today we're talking about something that sounds almost contradictory: low power and lossy networks, or LLNs, networks that are designed to be lossy. That seems counterintuitive.
Right? It's like advertising a car as occasionally unreliable or a restaurant as sometimes we burn the food. But here's the thing, LLNs are absolutely everywhere, and they're the reason your smart home works. Your city's power grid is getting smarter, and why industrial facilities can monitor thousands of sensors without going bankrupt on electricity bills.
Okay, so we're talking about the invisible backbone of the Internet of Things?
Exactly. And the beautiful part is that these networks take all the constraints, low power, packet loss, limited memory, and turn them into features, not bugs.
All right, I'm intrigued. Let's start with the basics and work our way up to the really nerdy stuff.
Perfect. Buckle up, because we're going on a journey from your smart light bulb to industrial power grids.
So, let's define our terms. What exactly is a low power and lossy network?
Great question. An LLN is a class of network where both the routers and their interconnections are heavily constrained. We're talking about devices that run on batteries, sometimes for years, with limited processing power, tiny amounts of memory, and wireless connections that are inherently unreliable.
When you say lossy, you mean packets get dropped?
Exactly. In a traditional network, we expect maybe 1 to 2% packet loss at most. In an LLN, you might see 10%, 20%, even 30% packet loss, and that's normal. The network is designed to handle it.
That sounds horrible. Why would we design it that way?
It's not by choice, it's by necessity. Think about the environments these devices operate in. A temperature sensor buried in a concrete wall of a factory, a soil moisture sensor in a farm field, a smart meter attached to your house. These devices need to run on a coin battery for 5 to 10 years, cost just a few dollars to manufacture, communicate through walls, metal structures, and not be affected by interference, and operate in extreme temperatures.
Okay, so the lossy part comes from the harsh operating conditions.
Right. And the low power part means we can't use traditional networking approaches. If your Wi-Fi router used the same power as a smart sensor, you could power your whole house for a year on an AA battery.
That's actually impressive when you put it that way. So, what makes these networks different from, say, Wi-Fi or Bluetooth?
Several things. First, the data rates are much lower. We're talking kilobits per second instead of megabits. Second, the duty cycle is extremely low. A sensor might wake up, transmit a few bytes, and go back to sleep for hours or days. Third, these networks can have hundreds or thousands of nodes in a mesh topology.
Mesh topology? That's where every device can act as a relay for other devices?
Exactly. Your smart light bulb isn't just a light bulb. It's also a mini router that can help relay messages from your smart thermostat to your hub. This creates redundancy and extends range without needing high-power transmitters.
So, it's like a neighborhood watch, but for data packets. Everyone helps everyone else.
I love that analogy. I'm stealing it. Yes, it's community networking at its finest.
All right, let's get into the technical weeds. What protocols and standards make LLNs work?
Oh, now we're talking. The foundation starts with IEEE 802.1 5.4, which is a standard for low-rate wireless personal area networks. Think of it as the physical and MAC layer, how the radio actually transmits bits through the air.
So that's the hardware layer. What about the networking part?
That's where things get interesting. The Internet Engineering Task Force, the IETF, created something called 6LOWPAN, which stands for IPv6 over low-power wireless personal area networks.
Hold on. IPv6? Like full internet protocol addresses on tiny battery-powered sensors?
YES. And this is actually brilliant. By using IPv6, every single sensor, every light bulb, every smart meter gets its own globally unique IP address. No NAT, no gateway translation mess. End-to-end IP connectivity.
But IPv6 packets are pretty big. How do you fit that on a network with tiny packet sizes?
Excellent question. That's where 6LOWPAN's magic comes in. It uses header compression to squeeze IPv6 headers down from 40 bytes to sometimes just 2 bytes. It also handles fragmentation and reassembly when packets are too big for the underlying 802.1 5.4 frame size, which maxes out at 127 bytes.
Okay, so we've got the physical layer and the adaptation layer. But how do these devices actually find routes to each other?
And now we get to my favorite part, it called RPL, the routing protocol for low power and lossy networks, defined in RFC 6550.
I love how network engineers just love their acronyms. Tell me about RPL.
RPL is a distance vector routing protocol, but it's specifically designed for the constraints of LLNs. It creates a tree-like topology called a DODAG, Destination-Oriented Directed Acyclic Graph.
Okay, you're going to need to break that down.
That's fair. Think of it like a family tree, but for data routing. At the top, the root, you have a border router that connects the LLN to the internet. Every other device in the network finds its position in this tree based on its rank, basically how far it is from the root.
So each device knows which direction is up toward the internet?
Exactly. And the beauty is that it's a DAG, directed acyclic graph, which means there are no loops. You can't have circular routes that would waste precious battery power sending packets in circles.
That's smart. What about when a device needs to send data?
RPL handles 3 main traffic patterns: multi-point to point, many sensors sending data to one destination, like thousands of smart meters reporting to a utility company. Point to multi-point, one source sending to many destinations, like a controller sending commands to multiple actuators. And point to point, 2 devices communicating directly.
Are you saying that all of this happens automatically?
Yep, RPL uses control messages, DIOS, DAOS, DISS, to build and maintain the routing topology. Devices advertise their presence, exchange routing information, and adapt to changes in the network.
DIOS, DAOS, DISS. Should I know what those are?
Only if you want to impress network engineers at parties. DIO is DODAG Information Object. Basically, hey, I'm here and this is my position in the tree. DAO is Destination Advertisement Object. I can route to these destinations. And DIS is DODAG Information Solicitation. Anyone out there? I'm new and need routing info.
It's like a very polite, very technical cocktail party where everyone is constantly introducing themselves and updating their contact information.
That's actually perfect. And just like at a party, sometimes people leave or new people arrive, and the network adapts.
Okay, so we've got the theory. Let's talk about where this technology is actually being used. What are the killer applications for LLNs?
Oh man, there are so many. Let's start with smart grids, probably one of the most important applications.
Smart grids. That's the electrical grid going digital, right?
Exactly. Utilities are deploying millions of smart meters using LLN technology, particularly 6LOWPAN and RPL. These meters form mesh networks where each meter can relay data from neighbors, creating a self-healing network that gets data back to the utility company.
Self-healing? So if one meter dies, the network routes around it?
Precisely, and the benefits are huge. Utilities get real-time energy consumption data, can detect outages instantly, can implement demand response programs, and can integrate renewable energy sources more effectively. Consumers get detailed energy usage information and time of use pricing.
And all of this on battery-powered or power line-powered devices that need to last for decades.
Exactly. Some smart meters are designed to operate for 20 plus years. That's why the low power aspect is so critical.
What other applications are out there?
Industrial automation is massive. Factory floors with thousands of sensors monitoring temperature, vibration, pressure, and flow rates. In the past, you'd need to wire all of these, which is expensive and inflexible. With LLNs, you deploy wireless sensors that form a self-organizing mesh network.
So a factory can just add sensors wherever they need them without pulling cables?
Right. They can also move production lines around without rewiring. The network adapts automatically. Major cost savings and flexibility.
Home automation must be another big one.
Absolutely. Your smart home is probably running on LLN technology. Thread, Zigbee, and even some Matter devices use 6LOWPAN and similar protocols. Your smart lights, thermostats, door locks, sensors, they're all forming mesh networks in your walls.
I never thought about my light bulbs having IP addresses and routing data packets.
Yeah, it's wild. Your smart light bulb is technically a router, but don't let it go to its head.
What about other applications?
Environmental monitoring is huge. Soil sensors in agriculture, air quality sensors in cities, water quality monitoring. Healthcare is emerging with remote patient monitoring. Smart cities use LLNs for parking sensors, waste management, and street lighting control. The list goes on.
It really is the invisible backbone of IoT. All these applications we take for granted are running on these constrained networks.
And here's the scale. We're talking billions of devices. Some estimates suggest there could be 75 billion IoT devices by 2025, and a huge portion of those are running on LLN technology.
Okay, this all sounds great. But what are the major challenges with LLNs?
Oh, where do I start? Let's talk about congestion first. Remember how I said RPL creates a tree topology?
Yeah, with the root at the top.
Well, that creates a bottleneck problem. All the nodes closer to the root have to relay traffic from all the nodes below them. So a node near the root might be forwarding data from hundreds of child nodes. This causes congestion, packet loss, and that node's battery drains much faster than others.
So the nodes doing the most work die first, which breaks the network?
Exactly. It's called the energy bottleneck problem. Researchers are developing solutions like load-balanced RPL variants that try to distribute traffic more evenly, but it's still an active area of research.
What about security? I imagine billions of connected sensors create a massive attack surface.
Yes, that is a huge concern. These devices have limited processing power, so they can't run heavyweight cryptography. But they're often deployed in unsecured locations. Anyone could physically access them. And they're handling sensitive data, your energy usage patterns, industrial process information, healthcare data.
So what's the solution?
6LOWPAN and RPL do include security features, authentication, encryption, and integrity protection. But implementing them on resource-constrained devices is challenging. There's ongoing work on lightweight cryptographic algorithms designed specifically for IoT devices.
What about mobility? What happens if nodes are moving?
Good question. Standard RPL doesn't handle mobility well. The protocol is designed for relatively static networks. When a node moves, it needs to rebuild its routing paths, which creates overhead and delays. There are enhanced versions of RPL for mobile scenarios, but it's still not ideal.
What other challenges are there?
Heterogeneous traffic is a big one. Early LLN applications were simple, sensors sending periodic temperature readings. But now we're seeing mixed traffic. Some sensors sending tiny packets every few minutes, others streaming video or handling command and control traffic.
And the routing protocol doesn't handle that well?
The standard objective functions in RPL, OF0, and MRHOF don't account for different traffic types. They might route high bandwidth traffic through already congested nodes. Researchers are developing queue-aware and workload-based objective functions to handle this better.
It sounds like LLN research is still very active.
Oh, absolutely. We've solved the basic problems, but optimizing for scale, heterogeneity, security, and energy efficiency in all these different deployment scenarios, that's the cutting edge.
So let's look ahead. Where is LLN technology going in the next 5 to 10 years?
I think we're going to see massive scale increases. Right now, a typical RPL network might have hundreds or low thousands of nodes. We're heading toward networks with tens of thousands or even hundreds of thousands of nodes in a single domain.
That seems like it would create even worse congestion problems.
It would, with current protocols. That's why there's so much research on hierarchical RPL, multiple DODAGs, and hybrid routing approaches that combine proactive and reactive elements.
What about integration with other technologies?
Great question. We're seeing hybrid networks that combine LLN technology with other protocols. For example, using 6LOWPAN for the sensor network, but having edge routers that connect to 5G for backhaul, or combining Zigbee, Bluetooth Low Energy, and 6LOWPAN in smart home environments.
Kind of like having different transportation systems, local roads, highways, airports, all working together?
What a perfect analogy. Each has its strengths and integration gives you the best of all worlds.
What about AI and machine learning? Are we seeing that in LLN management?
Absolutely. There's exciting work on using ML for anomaly detection, predictive maintenance, and intelligent routing decisions. Imagine a network that can predict when a node is about to fail based on battery level, traffic patterns, and environmental conditions, and proactively reroutes around it.
That would solve the bottleneck problem you mentioned earlier.
Exactly. And ML-based intrusion detection is becoming important for security. You can detect unusual traffic patterns that might indicate an attack, even with limited processing power on the devices themselves.
What about standards? Is everything converging?
Definitely movement toward consolidation. Thread and Matter are trying to create interoperable smart home ecosystems. The IETF continues to refine and expand the 6LOWPAN and RPL standards. But we'll always have some fragmentation because different applications have different requirements.
What's your prediction for the most transformative application in the next decade?
I think smart cities are going to be huge. Imagine a city where every streetlight, parking space, trash bin, air quality sensor, traffic signal, everything is networked using LLN technology. The data and automation possibilities are incredible. Real-time traffic optimization, pollution monitoring, predictive infrastructure maintenance.
And all running on low-power mesh networks.
Exactly. Cities that might have seemed like science fiction a decade ago are becoming reality, and LLNs are making it possible.
Before we wrap up, I want to zoom out. What's the big picture importance of LLN technology?
LLNs represent a fundamental shift in how we think about networking. For decades, we optimized for speed and reliability. We threw more power, more bandwidth, more processing at every problem. LLNs forced us to think differently. How do we build massive-scale networks under severe constraints?
And the answer turned out to be
Accept the constraints and design around them. Don't fight the fact that packets will be lost. Build protocols that handle it gracefully. Don't fight limited battery life. Make the network cooperatively distribute the burden. Don't fight limited processing power. Do the heavy lifting at the edge routers and keep the nodes simple.
it's kind of philosophical, working with limitations instead of against them.
Exactly. And the techniques developed for LLNs are now influencing mainstream networking. We're seeing ideas from RPL and 6LOWPAN showing up in other areas because they're fundamentally sound approaches to distributed systems.
What should our listeners take away from this conversation?
I think three things. First, the IoT revolution is built on these invisible LLNs, billions of constrained devices forming mesh networks and enabling smart everything. Second, networking isn't just about speed and bandwidth. Sometimes the most elegant solutions come from embracing constraints. And third, this is still an active field with huge opportunities for innovation.
And maybe next time you turn on your smart light, you'll think about the DODAG it's participating in.
Exactly, though that might make you sound a little crazy at dinner parties. Hold on, I need to check if my light bulb has a good rank in the routing topology.
I can see it now. Sorry, I'm late. My DODAG was reconverging.
New excuse, I love it.
All right, folks, that's our dive into low power and lossy networks. The technology you've never heard of that's quietly running the connected world.
This was fun. I don't often get to geek out about routing protocols for this long.
Well, until next time, stay curious, stay connected, and remember, even your light bulb is smarter than you think.